Now since we know how pressure varies inside a static fluid, now let's find the value of the force exerted by the fluid on any body which is submerged inside the fluid. Okay, so the topic is hydrostatic force on a submerged body. So this is the topic. So let's consider a body. Let's say this is my body and this is submerged inside some fluid. So let's say this is my fluid. Okay, and this is my free surface. Here is air. The pressure here is P atmospheric. Okay, this is the fluid. The body is submerged inside this fluid, so let's just write it. So this is my body submerged inside the fluid. Better just let's take it a bit above so that I can easily define my coordinate axis. So let's say this is my origin and these are my coordinate axes. So let's say this is z axis, this is y axis, this angle is theta, and since y cross z will be x, so x is pointing out of the plane. Okay, we are looking the edge view of the plate. So the plate is actually not of a particular geometry, it can be of any arbitrary geometry. So let's say this is any arbitrary shape. So since we are looking from the x-axis, if we look the plate from, let's say, here, okay, so if we look the plate from here, that is in the xy axis, how would it look like? So let's say this is my y, this is my x, this is my y. The plate in the xy plane would look, let's say, would have some arbitrary geometry, and this is the edge view, so that's why the plate is looking like this. Okay, let's take the density of this fluid as rho, and we assume that the density of the fluid does not change with pressure, that is, the fluid is incompressible and the hydrostatic law can be used for this fluid. So the pressure value can be found from the hydrostatic law, that is, the pressure at any depth h will be given by, if it is P atmospheric, then pressure at this point will be given by P atmosphere plus h rho g, right? Okay, we are interested in finding the total force that acts on this body. So we'll find the force by taking an elemental area. So elemental area dA, which would look something like this in xy axis. So we'll find the force due to pressure on this dA element and we'll just integrate over the entire area to calculate the force value, right? Now let's say the height, the depth of this elemental area be h. The force dF acting on this elemental area would be dF equal to PdA, where dA is the area of this elemental surface, right? So what would be pressure on pressure would be simply the hydrostatic pressure, which will be given by P atmospheric plus h rho g times dA. Okay, and the total force F will be simply integration over dF over the entire area A, which is P atmospheric plus h rho g dA integration over the area A. Now we will simplify this force expression in terms of the centroid value of my plate geometry, so that I don't have to always start from the beginning by taking the integration and all. And once I'll do this integration, I'll get in terms of the coordinate in terms of the centroids, and by just knowing the value of the centroid we can know the value of the force acting on that body, right? So now we will write H in terms of the, we'll try to write H in terms of the centroid values, and let's do it. So from this figure, what is H? What is the relation between H and Y? So y cos theta, y sin theta is H. Okay, so H will be y sin theta. Just write H in terms of y sin theta. So this will be integration over A P atmosphere plus H is y sin theta. So y sin theta rho g. Okay, times dA. Now we can take P atmospheric, since P atmosphere is independent of the elemental area that I have chosen. So this expression would become P atmospheric into the area of my body plus rho g y dA integral over A. Now if you think carefully, what is this dA? This dA would be dx dy. So that's why I cannot take y outside of this integral, right? Now if you see here, this expression can be written in terms of the centroid of the body. So what is the definition of the centroid of the body? So if I have some body, then let's say this is the centroid values of the body, then xc is given as 1 by A integration of x dA, and yc is given as 1 by A y dA integral over A. So now one integral over A y dA can be written as yc times A. So this will be written as P atmospheric A plus rho g into A yc, right? So now I have just written the force in terms of the centroid. So let's say if you are given any body whose centroid values you know, then you can immediately find the value of F from this expression. Okay, I can further simplify this expression as P atmospheric plus rho g into yc times A. This we can just write as PC times A, where PC is the where PC is the absolute pressure in the fluid at the location of the centroid, right? Now the most of the problems that you will encounter for finding the force on the submerged body will be like this. So you have a body, okay, now the fluid is, let's say, filled this body only feels the fluid in this portion, in this side, and air is in this side. So then what would happen? P atmospheric would act from this side as well as from this side, and that's why the net force will be just because of this rho g yc times A. So in that case we can simply write F net equal to rho g yc times A, where A is the area of this body. But the area of this body can be anything. It can be in the xy axis, it can be in xz axis or some other axis, or in some other plane. So what should this area be? So this area is actually the area which is, it is actually the area of the plane which is perpendicular to the pressure. Okay, so in this case my this area was perpendicular to the pressure. Since pressure, if you just see from here, pressure acts normal to the surface, so the pressure is in the z axis, and from here we see that the z is actually into the plane, so the pressure is actually normal to this surface, right? So that's why the area A is actually the area in the xy plane. So area is always the area of the plane perpendicular to the pressure. Okay, so this will be the net force that this body would feel submerged inside the fluid, when it is submerged inside the fluid. Actually there is some correction, so this y sin theta is actually hc, right? So I've done a mistake everywhere, so this would be rho g phi c times hc times a. So what is this hc? So let's say this so let's again see this body. So this body would be, let me just draw here. So let's say this is my body, okay, and let's say this point is my center of the body, is the point which corresponds to xc comma yc. Okay, so now from the point where there is free surface, this height would be hc. Okay, so this was your free surface, air was there. Okay, actually there is a correction in the video that I made. So I wrote that hc is yc. This is incorrect, but actually would be here. So I missed this sin theta term, and this would be yda, and yda is actually yc, and this sin theta would come, and this yc sin theta is hc, and that's why this expression would come. Okay, so this is a correction in this video. Now let's answer a question that, let's say if this is a body, so we had a body like this submerged inside the fluid, right? So now the question is that whether this force, the total force that we have found, whether that uniformly applies on the body or not. So the answer is it does not apply uniformly. And why? The reason is the hydrostatic pressure inside your fluid, and it varies with, as the depth increases, the force, the hydrostatic force also increases, right? Because the hydrostatic force was, the pressure was h rho g. So since force is proportional to pressure, this will be proportional to height. So as I increase this depth, so the force would look something like this. So it would be like this, the force due to pressure would be like this, then it would increase, further increase, and again would further increase. Okay, So this how the force profile would look like on the body. Thus this force is inhomogeneous, and since it is inhomogeneous, the net force, this net force that we have calculated, will actually not be applied on the centroid. Instead, if you just think geometry carefully, so let's say if this was my xc, the coordinates of the centroid xc yc, then since the force is increasing as we are increasing the depth, the center of this force will be actually somewhere down. So it would be somewhere, let's say here. Okay, and this point is called the center of pressure. Center of pressure, since this net force will be acting on this point and not on the center of the body. Now let's calculate the coordinates of the center of pressure. So we'll calculate this by using the concept of rotation. So if you just see the profile of the force, this force would have the tendency to rotate this body, right? And if this is your x-axis, then this force would try to rotate the body about the x-axis, right? Now if the coordinates of this center of pressure be xp, yp, then the torque applied because of this fp on the body would be given by fp times yp, because this yp is the perpendicular distance about this x-axis, right? And we are interested in finding this yp. So how would you find this yp? So you use the elemental areas. So this net torque on the body, so if this is the net torque on the body about x-axis, this should be equal to the integration of the torque on elemental area dA, right? So we'll just use this trick to find the coordinate value yp. So what would this be? This would simply be fdA. This would simply be y times df, right? And what was df? From previous arguments we know that df is pda, right? And considering this situation, when you have the ambient air on one side and the fluid on other side, my P would be simply H times rho g, and again since H is y sin theta, this will become y square sin theta rho g times dA. Okay, integral over a, so let's just write it here. So integration over a y square sin theta rho g dA, what would this be equal to? So now this angle is fixed, rho is not changing with area and g is also not changing with area, so that's why we can just take it outside. Sin theta rho g y square dA integral over a. Now this integral over y square dA, this has special name. This is called area moment of inertia. Okay, and since this is area moment of inertia, about x-axis, denoted by Ixx. So our expression would become f net. So f net times yp, this would become sin theta rho g, and not integration but Ixx. Okay. Now we will replace this area moment of inertia about x-axis Ixx in terms of known quantities. So how do we do that? We'll use the parallel axis theorem. So what does parallel axis theorem states? So let's say if I have a body, okay, so let's say this is my body, and let's say this is the axis which is perpendicular to my board, okay, and this body is rotating, let's say rotating like this around this axis. So parallel axis theorem tells me that the moment of inertia of this body about this axis Ixx. So in our case this was x-axis and this was our body, and the moment of inertia of the body about this x-axis was Ixx. So moment of parallel axis theorem tells me that this Ixx can be written in terms of the moment of inertia about the centroid of the body plus, if this distance, if let's say d, then this term will be a times d square. And in our case, what is this d? What is the distance of the centroid from the x-axis? This is nothing but yc. So that's why this will be written as a yc square. So now we will plug in this value in this expression. So this will become sin theta rho g I want to understand about centroid plus a yc square. Now using the expression of f net, so what was f net? F net was rho g hca. Just use, so yp will become, this will be rho g hc times a. Now we replace hc with, so what was hc? Just see the figure. What was, how can we write hc in terms of yc? So the relation between y and h is y sin theta is h. So hc will be yc sin theta. Just write hc is equal to yc sin theta. Simplifying this expression, what would become? So it would become Ixx sin theta cancels out with sin theta, rho cancels out with rho, g cancels out with g, and this becomes Ixx upon a yc plus a would cancel out with a, yc would cancel out with one yc would cancel out with this yc, so this will become yc. Or just rearranging this would become yc plus Ixx upon ayc. So this is how you find the coordinate y for your center of pressure. Okay, so now the question is that, is torque only about x-axis? So let's see this figure. So this is, okay, so let me just see this figure. Okay, so from your high school you know that torque, or just write torque. What is torque? Torque is r vector cross f vector, right? Or what we usually write it like, this is the perpendicular distance of force times force acting on that body, right? Now you see this body and what is the force on this body and what is the direction of the force on this body. So as I told earlier that, so this is your z axis, right? Okay, so if this is your z axis and the force is into the plane because the pressure is acting, so this is your pressure, this is acting along z axis and z axis is into the plane, so that's why the force will be into the plane. So the perpendicular distance of this force can be this or can be this, right? So it can be either y or also can be x. So the torque will be along x-axis and will be along y-axis. So that's why you will use this concept to find the x coordinate of this center of pressure. Okay. So now again we'll use a similar analysis. So we will say that let's say this xp. Okay, just let me write it. So now to find xp, okay, so we'll again use a similar analysis. We'll write xp times f net, that would be equal to integration a and x p dA, right? Is it clear? Okay, so now we will again write we'll again assume so now since we are assuming that this is our body and on one side of the body there is this ambient air and on the other side there is a fluid, so that's why we can write p, so p naught will not come and we can write just p equal to h rho g. So we can just write it integration over a x, what would be p would be again h rho g times dA. Okay, now what is h? H is y sin theta, we'll have x y sin theta rho g dA integration over a. Now again rho g and sin theta are independent of this elemental area that we choose, so that's why this will become rho g sin theta xy dA integration over a. This integration over a xy dA is called the product moment of inertia Ixy. So this is I product moment of inertia Ixy. So this will become rho g sin theta Ixy. Now again using the parallel axis theorem for this product moment of inertia, we can write this as rho g sin theta I xy plus xc yc times a. Okay, so writing the expression for f net. So what is the expression for f net? F net is rho g hc times a. Rho g hc, sorry, g is gravity, rho g hc times a is equal to rho g sin theta I xy plus xc yc times a. This rho g would cancel out with rho g, xp would be sin theta by hc. Now what is hc? hc is yc sin theta times a I xy plus xc yc a. Sin theta would cancel out with sin theta and this would simply become xc plus I xy by yca. Okay, so this is how we'll calculate the center of pressure coordinate xp. So we'll have the knowledge of moment of inertia, the product moment of inertia, we'll have the knowledge of the centroid xc and yc, and we'll calculate xp and similarly yp. So what was yp? Yp was yc plus I xx upon yc times a. Okay, so these are the two center of pressure coordinates xp and yp. So from this lecture we are now able to find the net force value on a submerged body, and also the point of action, or called the center of pressure, on the body. Okay.